All right, welcome back to the induction and recursion slides. I'm very excited. This is a very fun topic for me. So we were talking about sequences, just numbers in order, and that's going to lead to this concept of induction that we haven't really gotten to yet. I just gave you a sneak peek, but we've learned a little bit now. Let me talk to you a little bit more about sequences before we get to induction. So there's a bunch of different ways that you can still describe sequences. They can be increasing, non-decreasing, decreasing, non-increasing. They can also be geometric and arithmetic, and these are probably terms that you've heard of before from like a math class. So a geometric sequence is one where things are getting multiplied. They're getting like bigger because you're multiplying the next element by the previous element turns into the next element by multiplying it by something. Okay, it can get smaller, I guess, but it's a multiplication. That's what it means to be a geometric sequence. It's a sequence where the the next element of the sequence is defined in terms of the previous one. So ai plus 1 is equal to ai times some r, and r is called the ratio, the common ratio that like links them all. And geometric sequences can be finite or infinite, not a problem. So if you define, you need to give a starting number. So let's define that our starting number is 1. That's like a0. Our sequence index 0 is 1, then you can get all the rest, right? Because you know that a1 is equal to, following this pattern, it's equal to r times a of I, and we have to pick an r, I guess. So let's say that r is 2. So a1 then equals 2 times a of 0. 2 times a of 0, which is equal to 2. So we know that the next element in the sequence is 2. And it's just, well, to get to the next one from this one, you multiply it by 2 again. So this becomes multiply by 2 to get 4, multiply by 2 again to get 8, and then you just keep going. 16, 32, 64. That leads to an infinite sequence of all the powers of 2. See that? So that's a geometric sequence. It's like you have a ratio in common. The ratio could be fractions, so I guess it could get smaller, but a lot of the time we think of it as a number that's bigger than 1 that you're multiplying. Okay, so that's a geometric sequence of very similar ideas in arithmetic sequence. That's a sequence where the next one is the previous plus some number. We call that the difference between elements. It's called the common difference, all right? So the sequence can be finite or infinite again, so let's give like a finite arithmetic sequence. So let's be like our starting element of the sequence, let's call it sequence number b, sequence b. So let's say that 2 is the first element, so b0 is 2. And then we'll say that this sequence has 5 elements, so it stops. That is horrible handwriting. Let me fix that. This sequence has 5 elements. Alright, how do we get to the next one? Let's say that our difference, our common difference, is 2. So d equals 2. So starting from here, we can get to b of 1 now. What's b of 1? It's equal to b of 0 plus d, which is 2 plus 2. So it becomes 4. That's the next element. And then to get to the next one, you're just going to add another 2, right? So 6 is the next one, right? So you add 2 plus 2. So it makes 6, then 8, then 10, and this is b4, right? It goes only to 4 because we're going to say this is a finite sequence. It only has 5 elements, all right? So that's an example of an arithmetic sequence. It's essentially plus versus times. Geometric is times, arithmetic is plus. Hopefully that's not too bad. Okay, so you can define sequences in terms of other previous elements. Technically, you can do that for Fibonacci, right? It's defined in terms of the previous 2 elements to get to the next one. Woohoo, that's fun. So here's a sequence. I would like you to describe it to me, please. So here are some terms. Like circle which of these apply to this particular sequence, all right? Or you define the sequence like this. A of n is equal to n squared minus 2n, and the first n is 1, so its index, it starts at a1. So a1, a2, it's an infinite sequence. It just starts at 1 though, all right? So use these terms. Here's the slide with the definitions to describe that sequence, please. All right, let's calculate some terms of the sequence. A1, A2, A3, A4. A1 is equal to, well, it's 1 squared minus 2 times 1. A2 is 2 squared minus 2 times 2. A3 is 3 squared minus 2 times 3. A4 is 4 squared minus 2 times 4. See the pattern? So what are all these? This is 1 minus 2, so that's negative 1. This is 4 minus 4, that's 0. This is, let's see, 9 minus 6, that's 3. This is 16 minus 8, so that's 8. And it looks like the difference is always going to keep getting bigger because 2 times something versus something squared, it's always going to win out. See how the difference keeps getting larger and larger, the distance gets larger and larger. So, well, what's true about these guys? Well, like this is less than this, is less than this, is less than this. So it's totally, for sure, increasing. So this is an increasing sequence, right? It could also be, though, you see how it's also, like, if it's less than, it's totally also less than or equal to 2 for everybody. So it's also non-decreasing. Do you see that? According to the definition, all it needs is, like, it's got to be less than or equal to when you compare consecutive elements. So that's totally fine. The ones that it's not, though, is definitely not decreasing, because these numbers are getting bigger. And it's not non-increasing, because it's either they stay the same or they get smaller. And they're definitely getting bigger every time. So that's not going to count. So increasing and non-decreasing both describe the sequence, okay? So that's that. I guess, essentially, increasing implies non-decreasing. Hope you see that. All right, let's talk about Fibonacci, because you can totally use the same idea like we were doing here for defining things in terms of previous elements. For Fibonacci, it's just not the previous element. You use the 2 previous elements. Right, to get to the Fibonacci sequence, it's like the sum of the 2 previous things. So that's called a recurrence relation. It's when you define a term of your sequence as a function of previous terms in the sequence, potentially many. All right, because the Fibonacci sequence is really a recurrence relation. It's just like, here are the 2 first values. It's all you needed. You needed the two first terms in the sequence, and that kicks you off. Like that's f of 0, this is f of 1, and then any other term in the sequence, you can calculate it from the previous 2. F of n is equal to f of n minus 1 plus f of n minus 2. Do you see that? Because what is this? This is equal to the sum of 0 plus 1. That's your next element. That's 1. And then if you sum these guys, that gives you the next element. That gives you 2. And you keep going. 1 plus 2, that makes for you 3. And that's the next element. Then 5. Then 8. And so on and so forth. Do you see how you can define it like that? That's how you can define the sequence. That's another way of doing it. That's called a recurrence relation. And you could, technically, geometric and arithmetic sequences are special cases of recurrence relations. It's just when you define it in terms of previous elements, or just defining them in terms of one previous element for arithmetic and geometric sequences. See how an arithmetic sequence, it's like, all right, here's your starting value, and every other element of your sequence is like this. It's the sum of the previous one plus the difference. So that's how you turn that into a recurrence relation. And then like your geometric sequence, again, it has a starting value, and then for every other element of the sequence, like it's defined in terms of the one that came before it times this constant r, your common ratio. Cool. So yeah, those are recurrence relations in a nutshell. Here's a practice for you. So here is a sequence that's defined like this. So the first 2 elements of it look like this. And then every other element from index 3 onwards, because it starts at 1, are defined like this. Please give the first 6 terms of this sequence. That's really just doing some math. Hopefully it's not too hard. But like here it is. The first ones are 1 and 3. Did you do the rest, hopefully? So, all right, the next one, b of 3, is defined in terms of the previous 2 elements, is defined in terms of 3. If n is 3, n minus 1 is 2, so it's b2, minus 7 times n minus 2. If n is 3, n minus 2 is 1, times b of 1. Okay? So let's calculate that. So b of 3 is equal to b2. This is b1, this is b2 right there. Let me space those out a little bit. I don't like how close they are. Can I? I can. Nice. There. This is b1, this is b2, and so we're calculating b3 from those. So it's equal to 3 times 7 minus, 3 minus 7 times 1. So that's 3 minus 7, so that's negative 4. So apparently B3 is negative 4. And then to get the rest, like what goes here, well, it's going to be all the previous element, negative 4, minus 7 times the two elements ago, 7 times 3. So that's negative 4 plus 21. That's going to be, it's times positive 3, excuse me. So it's negative 4 minus 21. So that is negative 25. Cool. And then this one, what does this one become? This is going to be equal to negative 25 minus 7 times negative 4. So that's going to be like plus positive thing. So negative 25 plus 28. So that becomes like 3 again. Isn't that crazy? So it's like going all over the place. And then this one is going to be what goes here. This is apparently the sixth and final term that we care about right now is going to be 3, the one before it, minus 7 times the one that came 2 before that. Minus 7 times negative 25. And I did that ahead of time. That's apparently, what is this? This is 3 plus a bunch of things. 3 plus 175, essentially. So that's 178. Did you get that? So that's just defining sequences in terms of a recurrence relation. Not too horrible. Let's next talk about something you can do to a sequence. You got a bunch of numbers. You can add them all up. So that's called a summation. So there's this fancy notation called summation notation that makes it easy to talk about, I want to add up a bunch of stuff. Let's talk about the sum of all the terms in the sequence. This is how you do it. It's like, all right, Greek capital sigma, because that makes an S sound in Greek. It's like sum all the values, and you got your indices. This is your mathematical for loop of all these elements from starting from index S all the way to index T inclusive. So this is like the start, and this is the end, including that one. It's inclusive. And it's like add up all the A of i's. Add up A of I plus A of I plus 1 plus A of I plus 2 all the way, where it starts at S. So A of S, S plus 1, A of S plus 2, A of S plus 3, all the way to A of T. All right, I'll write that out in a second. So here it is. Pretend we have this sequence. All right, we have A of 1, A of 2, A of 3, all of these ones, but I want to pick out a certain fraction of them. I want to sum out just the values, only the elements between AS and AT, so starting and ending, okay? So instead of writing this, like you could write it out, like I want this number, A of S plus 1 plus A of S plus 2 plus all those things, all the way to A of T. Instead of that, you can shorthand it, and you can write this instead, all right? This is saying, add up all the A of i's, where I starts at S, gets bigger by 1 each time, and ends at A of T. All right, see how this turns into this expressions. Add up all these numbers starting at A of S plus A of S plus 1 plus A of S plus 2 plus A of S plus 3 all the way to A of T, where T is your ending place, okay? So I is called the index. We probably got that in computer science from that. S is your lower limit. This is where it starts. And then T is your upper limit. You can put numbers here. I just called them S and T. This could be like 4. This could be 42. You could totally put numbers there. It's essentially a mathematical for loop that's always getting bigger by 1 every time. All right. So let me have some examples here. Let's express the sum from the numbers 2 to 55. All right. So you could totally write it like this. This is the number that I want. I want to calculate 2 plus 3 plus 4 plus ... plus 54 plus 55. You could write it out like that, and somebody would understand what you wanted. Or you could use summation notation. You could be like, all right, I want the sum of all the numbers. Let's use j as my variable. Starting from 2 all the way to 55, start j at 2, iterate all the way to 55. What do you want to do with j each time? I want to just sum the value of j as it changes. See that? So I can just say j. Do you see how that's going to turn into this? Because j starts at 2. So it's first is 2, then it's 3 plus 4 plus 5. It's summing. The sigma means sum. Plus 5 all the way to 55. So it adds them all up. Okay. One thing that we want to do a lot is to pull out the first term of a sequence, of a summation. And so here's how you do that. So let's say that we have, like, we want to separate. We have this sequence. Oh gosh, what's wrong here? Let me use my mouse. Say we got this guy. Oops, copy paste. So there's just it all written out again. Boop. Okay, it's back to normal. Let's say that we want to pull out the first term. Like we want to take the 3 all the way to 55, but we want to just like have the 2 sitting by itself. So let's pull out the first term of this summation by saying, well, it's 2 plus, then everything else, 3 to 55. How do you write that? How do you change this to mean add up all the numbers from 3 to 55? Well, it's another sigma, another summation, where j starts at 3 this time to 55. Still adding up all the j's though, but j starts at 3 now. See that? So that is how you pull out the first term of a sequence. You can also think about pulling out the last term. This is something we will want to do eventually. It'll make proofs go through. And then finally, we talked about this actually just briefly, last slides, because I told you there was a closed form for a particular kind of summation. We just didn't have those words, essentially. But sometimes we don't need to use this summation notation to talk about a sum. All right. So instead, there is a closed form for certain kinds of sequences. So here's a closed form for terms in this following arithmetic sequence. So if you have an arithmetic sequence that gets bigger each time, it looks like this, right? Because it's your starting value plus like some k plus d. So it's just a bunch of multiples of the difference as it gets bigger. So if you want to add up a bunch of elements of an arithmetic sequence, from like the first element all the way to, like, you want to add up the first n elements of the sequence, so from 0 to n minus 1, think of this. I hope you can see that that's going to be an arithmetic sequence, summed out. This has a closed form that looks like this. Apparently, if you just want the answer, it's a times n plus all this stuff. D times n plus 1, n minus 1 times n over 2. That is apparently the answer. So let me prove that to you, just for a simple case, where a is 1, d is 1, and n is 5. So let's say that I want to show you this. I want to show you the sum of these numbers, right? Where k starts at 0, goes to n minus 1, so 4 goes to 4. I want 1 plus k times d is 1, so 1 plus k. Okay, I want the sum of all those things. What is that, by the way? That's going to be, well, it starts at, if k is 0, it's going to be 1 plus 0 the first time, so that's just 1. Then when k is 1, it's going to be 1 plus 1, so that's 2. And so you see it's just the numbers, 1, 2, 3, 4, 5. And apparently, according to this, you could do it. There's a closed form, but the secret is, the proof is, like, what is this? The formula goes like this. It's a times n, so it's 5 plus d times, this is disgusting, it's going to be d, all this over 2. D is 1 times n minus 1 is 4. 1 times 4 times 5, which was 5. Or times n, which was 5. And so with all that, which is, I guess, 20 over 2 is 10, so 5 plus 10 is 15. So this answer is 15, and let me prove to you why this formula works. It's gonna do the right thing. An easy way to get this sum is to quickly add it in reverse. Add the whole thing all over again. Add this whole sequence to itself, but add it in reverse so that they line up. 5 plus 4 plus 3 plus 2 plus 1. When you do that, do you see how it's just a bunch of 6s? They all line up and they make 6. So it's 6 5 times. 6 plus, this turns into, when you double count the sequence twice, 6 plus 6 plus 6 plus 6 plus 6. But you double counted because you added it to itself again. That just made it easy, though. You do that all that over 2. So that's the closed form. The easy way to notice that is well, it's 5 6s over 2, which, yes, that's 30 over 2 is 15. So that's some proof that this is going to do the right thing for you. And then here's another one. Here's the closed form of the sum of terms in a geometric sequence. This is a cool one. It has to do with powers, of course. So let me prove to you this case. Apparently, if you had this geometric sequence and you wanted the sum of the first n terms of it, this is the answer. Very weird. Has to do with the ratio. Ratios of the ratio. So let me show you this for these particular cases. Let me show you the sum and how to think about it in general if you don't trust this yet. So k equals 0 to n equals 5, so up to 4 again, of, let's say that a is 1, so it's just r is 2, r to the k, 2 to the k. So it's just a sum of a bunch of powers of 2. So what do I want? Well, this is going to be 2 to the 0 plus 2 to the 1 plus 2 to the 3 all the way to 4, right? 2 to the 4th power. So what's this going to do? It's going to compute this, right? This is going to be 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th. And let's call all that, just like that is the answer. That's what we want to compute right now. But there is a closed form. Let's call this the sum, the original sum s. That's that. The trick is to notice why this works, the hand-wavy proof for why this shorthand works. Let's take this sequence and let's multiply it by the ratio. Let's compute r times the sequence sum s. So if I multiply this by another r, that just multiplies everything by another 2, right? So that becomes 2 to the 1, right? Just factor in the 2, distribute the 2. 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. And then let's compute the following. This is the trick. Compute r to the s, r times s, so r times the whole sum minus the original sum. What is that going to do? Do you see how, if you take this and you subtract this from it, you're suddenly, well, minus the 2 to the 1 cancels, minus the 2 to the 2 here cancels, 2 to the 3, 2 to the 4, those cancel, and it leaves these two terms. It's 2 to the 5th, because that's from the first, the rs, minus this one, because we were subtracting this thing, minus 2 to the 0. So that is your closed form. And, well, we wanted the real answer. This is r to the s minus s. How do I get the real answer? Well, just notice that what is r times s minus s? You can factor out an s from that. So this is r minus 1 times s equals 2 to the 5th minus 2 to the 0th power. And so if you divide this calculation over r minus 1, then you get the answer. And r minus 1 is just 1, so this is the final answer. Okay? I hope that makes sense. 2 to the 5th. I'm bad at drawing 5s today, apparently. Minus 2 to the 0. Right? And so that's kind of why this looks like that. That's a hand-wavy proof for you. But those are closed forms. And yeah, I want you to try this now. Using summation notation, so just the idea of summation. Here's the slide on summations. Please express the following. The sum of the squares of the odd integers between 0 and 100. So I would like you to compute, make a summation that represents the idea of 1 squared plus 3 squared plus 5 squared, all the odd numbers up to 99 squared, essentially. All right? So see if you can get that working. So there's a bunch of moving parts here. It's like the sum of what? So it's the summation, the squares of the odd integers between 0 and 100. So essentially, if you think about this in terms of programming, essentially a summation is like a loop. And so we need to iterate between these numbers, only the odd ones though, and square them. Sum all that. Does that make sense? So I'd like to loop between all the odd numbers, right? Let's make a loop that goes through all the odd numbers. So that's I equals 0. Let's say all the odd numbers look like this. If I is 0, I want to compute 1. If I is 1, I want to compute 3. So it should be 2 times I. See that? As I gets bigger, it's going to go to the next odd number, the next odd number. So this will make odd numbers. See that part? Makes odd numbers. I want the arrow to be next to each other there. This makes odd numbers. And then, well, I want to make all the way from 1 to 99. So what's 99? I think it's 49. It's 1 plus 49 times 2, I believe, is going to make 98, right? Plus that extra 1 makes 99. So that'll make the odd numbers right now. And I want the sum of their squares. So I just need all of this squared. See that? So that's going to be our final answer. That's how you just express the summation. That's all we're trying to do with this notation. Okay? So, if we are happy, let's move on now to the magic, the thing called mathematical induction. It's very, very powerful, very, very cool. It's essentially this domino idea, and it's very, very powerful. All right? So, we've been talking about sequences. Wouldn't it be nice to prove something about the entire sequence, about every element of the sequence at once? All right? So we can do a lot. We can cover a lot of sequences and express a bunch of different properties and prove them with our existing proofs. We have proofs about normal functioning logical things, right? We have for all proofs. That's essentially what we're doing. For every index, this is true about that thing, about that element. But there is something very powerful that gives you essentially a way to do a for all proof. That's what we're doing. Like, we want to prove something about every element of the sequence. It's essentially a for all proof. There's a cool tool we don't know yet. It's called induction, mathematical induction, right? And the reason that you need it, the reason that you might want to prove something about a sequence is that so you never get yourself mixed up thinking that one thing's true when it's not. So here's a theorem that's not true. It would be nice if it was. For every n squared plus n plus 41 is prime. This is a false theorem. All right, it's not true. But if you try a bunch of examples, if you try a decent number of examples, it is true. So here's here in Racket, if I include the number theory library, it lets me check for primality. So here I am ranging between numbers between, let's do 1 to, let's do 1 to 21. All right, 1 to 21, and okay, sure, Racket. False theorem.racket. It is true for all of those numbers. This sequence, defined in terms of the n squared plus n plus 41, here I am computing that. N squared plus with n plus with 41. There's the n element of the sequence if it's prime. It is prime. It's generating essentially prime numbers. Crazy. Okay? You have to wait. Let's go to 41. Oops. 41. That might make you think that, oh, this is always going to work. But no, this is when you really need to prove. You need to actually prove this kind of stuff, right? You need to prove once and for all. This works for the first 39 elements of the sequence. You have to wait until you get to the 40th element before it computes a number that is not actually prime. That's crazy. It works very well. This sequence works very, very well. But it doesn't generate it doesn't only go through prime numbers, all right? So you might think it checks out, but you can't just trust examples when you're trying to prove a for all, essentially. Does that make sense? And so we need cool ways to prove for alls, and we have a few, but a very powerful way is called mathematical induction. All right, so this is when you want to prove something's true for essentially, you can always define things in terms of natural numbers. So let's say that we want to prove a property for every natural number. We have a predicate. We would like to prove Pn for all n, where n is a natural number. So we want to prove P0, P1, P of 2, all the way for infinity. Okay. What we need, one way to do it is to use mathematical induction. What it gives us, the principle of mathematical induction, it gives us a way to do that. All right. It tells us that P of n is true for every n, for every natural number n, if you can prove to me separately the following two things. Prove that this is true, and prove that this is true. So you need to show that P of 0 is true. That's called your base case. That has some huge, huge ties to recursion, I hope you see. So you have to prove that the P of 0 is true, prove that the first thing works, and then you have to prove this simpler for all. Prove that for every k in the natural numbers, P of k implies P of k plus 1. Like the previous proof gives you the next proof. That's what you're doing. You can use the previous proof as firepower to get to the next proof. If you can show that this is true, that's called your inductive step. Both of these combined proves that P of n is true for every n. Okay? You see that? This is P of k implies P of k plus 1. It's giving you this. You can go from here to here. That's what it's saying. Okay? Let me draw you a picture for why this works. Or at least I'll write out some ideas. All right? Let me prove to you why this is going to give you P of n for every n. So if you prove P of 0 is true, that's your base case, then you have that at your disposal. Like you have that P of 0 is true. And then if you've proven this for every k in the natural numbers, P of k implies k plus 1, you know that P of 0 is true. You could run that through this proof now. You could run that through this idea. You know that, well, 0 is a natural number. Just plug in 0 to this, and I have that, well, P of 0, it gives you a proof for P of 0 implies P of 1. See that? But both of these together, you could plug in the P of 0. You know that P of 0 is true, and that proves to you then that P of 1 must also be true. Do you see that? You can plug it in. So you can go from P of 0, once you have that, that kicks off the magic of mathematical induction. You can use this one for the rest of time, just set k to 0, that feeds you out the P of 1. Do you see that? Because you can plug it into this implication and get out that P of 1 must have been true then. And now you have P of 1 at your fingertips. You can plug it in again here. You can set k to 1 and get out that P of 1 implies P of 2. Feed it in, you get P of 2 at your disposal, at your fingertips. And then you just keep on playing this game. You can feed in P of 2. That can make for you, like, think of it as a factory. It's producing P of 3 from P of 2. Now you have P of 3 to work with. You can plug it in to the inductive step to get out that P of 4 must be true. And this is always going to give you the next one. Do you see that? So you're always going to get the next number in the sequence, and you're starting at 0. It's not stopping. It's going through every natural number. All right? You see that? That's the goal. And so kind of the inductive step is the powerful one. And that's the hardest one to prove of these two. The base case is usually easy. Just like try 0, make sure it works. This one's the harder one. But what you do in the inductive step is you say you're proving P of k implies P of k plus 1. All right? For every k. And so it's a direct proof. What you do is you assume this and prove that, right? It's just as you would expect. It's a direct proof. So you get to assume that P of k is true and use it to prove that P of k plus 1 is true. All right? And so it is just a normal direct proof, but because it's so popular, mathematical induction is so popular, and like people are doing this direct proof all the time, this assumption, assuming that the smaller number works out to use it to build the bigger proof for the bigger number, this is called the inductive hypothesis. Assuming that P of k is true, that's called your inductive hypothesis. It really is just a direct proof, though. That's all. Right? So your book likes to start n at 1 when it's proving things for all positive, and it like proves things for all positive numbers. I think it's better this way because it's like natural numbers now. But the starting point, it's just like an infinite sequence that starts somewhere. So the starting point makes no difference at all. It's not a big deal. Okay. So that is mathematical induction. You got these two pieces. The base case, got to prove that. Got to show that the inductive step also works. And in proving the inductive step, you get to assume P of k as you're trying to prove P of k plus 1. And P of k, that assumption is called your inductive hypothesis, right? So you'll be using the inductive hypothesis. So here is just the quintessential example of mathematical induction. Let's prove that for all n greater than or equal to 1, this is true. So we're going to prove the closed form of this summation. The sum of all the numbers from 1 to n is equal to n times n plus 1 over 2. All right, so that's something you might have seen before. But we're going to prove this. We're going to make sure it works. For every n greater than or equal to 1, we're going to prove this once and for all with induction. Okay? So first of all, like an induction proof it's essentially a for all n P of n proof. So where is P of n here? It's like for all n where this is true about n, this is your P of n. You see that? This is what we're trying to prove for each n. The sum of all the numbers from 1 to 10 is this. The sum of all the numbers from 1 to 11 is this. For every n, this checks out. So there's my P of n. And then, all right, we need to prove the base case, the inductive step, or we need to like write down the base case and the inductive step, and then we'll prove them both. All right. So the base case is P of 0. We've got to show that that works. So base case, that's P of, or I guess because we're starting at 1, like it's P of 1 here. So we got to do that, and that is like we got to show that the sum of all the numbers from j equals 1 to 1, right? So we're plugging in 1 to our P. J is equal to, well, 1 times 1 plus 1 over 2. 1 times 1 plus 1 over 2. We've got to show that that checks out. That's their base case. And then the inductive step is you assume, right, for all k, p of k implies k plus 1, p of k plus 1. So p of k gives you p of k plus 1. All right, so that's, those are the two pieces. Let's prove them both. So this one, if you just spell it out, what's p of 1? It's that. It's like, all right, the sum of all the numbers, all the j's from 1 to 1, it's just 1, yeah? And then this is going to be equal to 1 times 2 over 2, which is 1. So they are both 1, okay? We just need to show that it works, because that proves the statement is true, right? The predicate's true when n is 1. So that works out for that one, QED. And then we need to do the inductive step. That's the harder one. So you get to assume, like you're proving this for every k. Assume this is true. It's a direct proof. Try to prove that. So what we do is we assume p of k is true. What does that give us? So what is p of k? It's this, where k is plugged in. So we know, based on our inductive hypothesis, our assumption, so what do we have? We have that k, with the sum of all the j's up to k, and we're plugging in p of k right now, is equal to, or n is k, k times k plus 1 over 2. Okay? And so this is what we get to assume as we're trying to make our proof happen. We get to assume that is true. And that's called our inductive hypothesis. All right, inductive hypothesis. Or people like to abbreviate this as IH for short. Okay? And then what we need to show now, we need to show that p of k plus 1 is true. All right? We need to show that p of k plus 1 is true. And so we need to show that the following is true. What's that? We need to show that the sum, well, just plug in k plus 1 for n now, the sum of all the j's up to k plus 1 is equal to, that is a j right there, by the way. Sum of all the j's up to k plus 1 is equal to, well, plug in k plus 1 here. It's k plus 1, it's a lot of math, times k plus 2, right, k plus 1 over 2. And so that is what we got to show, and we get to use this as firepower. We get to assume that that's true. Okay, so let's write this out. So here we have our inductive hypothesis. I'll write that out because we need that. That's our p of k. That's saying that, I'll just reproduce it on this slide. This is saying that this is true, this sum right here. The sum of all the j's, starting at 1, up to k, we get to assume that that is equal to k times k plus 1 over 2. And that what we need to show is our p of k plus 1, which is this plug in k plus 1 into this. All right, it's all this right here. We need to show that the sum of all the j's up to k plus 1 this time is equal to k plus 1 times k plus 2 over 2. All right? And so we can use this to show this. And so like starting from here, do you see how to kind of get it into looking like this? Could you get this to look like this? You can, can't you? That's going to be your secret. So this is what we need to start with. The sum of all the j's starting at 1 up to k plus 1. What is that? Let's take out the last term. Let's take out the k plus 1th term. Do you see how this is equivalent to the sum of all the j's up to just k plus that final element? It would have been when j is k plus 1, just like let's add that on the side. See the magic in that? So now I have this that looks like this, and I know what that's equal to. I'm assuming that's equal to that. All right, so let's replace. Using the inductive hypothesis now to replace this with what I'm assuming it's equal to. This is equal to k times k plus 1 over 2 plus that extra k plus 1 here. And let's get 2 as the common denominator here, so that's equal to k times k plus 1 over 2 plus k plus 1 over 2. Now I can bring them all together. this is what? This is equal to, well, if you do enough math, you can bring out a, let's see, you can bring out a k plus 1 of each of these, because this is, oh, sorry. I'm supposed to find a common denominator. This is 2 times k plus 1 over 2. Excuse me. So you see how you can take out, it's really just, this is all in one line now. You can take out a k plus 1 from each of these. So you can take out a k plus 1. And what's left? Well, there was a k and there was a 2, so it's k plus 2 times k plus 1 over 2. And that's what I need to show. I just showed it. So just like magic, I proved it. So this, I need to start here and end up here, using this along the way, and I did. I started here, and I got to this. They are equal now. QED. That is my inductive step proven. I've already proven the base case. Those are the 2 pieces I needed, and so therefore, just by the principle of mathematical induction, for all n, P of n is true. I have just shown this. It's done. Isn't that beautiful? It seems like it ended too soon, but that's all you needed, because now it can kick itself off. Like you have the P of 0, you can use your inductive step to get out the P of 1, to get out the P of 2, and build those proofs. You can always go to the next thing. You can always go to the next thing. That's what the principle of mathematical induction shows you. Gives you that. That's lovely. So next, let's talk about how to use maybe induction to define something. That's also a possibility. So let's define the natural numbers. You can do that essentially with induction. This is an inductive definition. It's not the same as like an inductive proof, but it's the same idea of like using previous things to build up the next thing. Kind of like our inductive step. All right. So let's define the set of natural numbers. The way that we'll do it is we're gonna it's like a variable that'll keep getting replaced. Let's start out with the first natural number. Let's start out our set of natural numbers with just the number 0. And then let's do the following. Let's pretend we can do the following. Until the end of time, forever and ever and ever, infinitely many times, we're going to take the largest element, call it n, out of our set S, whatever it is right now. Take the largest element out and add back in, well, keep the other one there, and add in n plus 1 as well. All right? If you do this, if you start with this, and you keep doing this rule, keep running that rule infinitely many times, S will hold every natural number, and therefore S is equal to the natural numbers. Right? So this is kind of like what it's telling you to do. Like say S is just the set with 0 in it. Go and find the largest element, that's 0 right now, and add back in that element plus 1. So this is like add in 1 now. And now S is equal to 0 and 1. And then it's like, all right, do that again, infinitely many times. Take out the biggest element, now that's the 1, and add in that plus 1. So now add in 2. So S is now equal to 0, 1, and 2. Do you see how, if you ran that rule infinitely many times, S would eventually become the natural numbers, if you could do that? That's your inductive definition. That is actually how you define the natural numbers, the set n. And yeah, so let me show that to you. It's an inductive definition. It's very similar to an inductive proof. There's again a base step and an inductive step, base case inductive step. So this is how you define the natural numbers. Like, all right, the base case, the natural numbers start with 0. 0 is a natural number. Claim that. That's true. And then the inductive step is, all right, if you have some n, if you know a number, n is in the natural numbers, then that number plus 1 is also in the natural numbers. See, this will eventually pick out the max as well. It works for any number that's in the set. Like if you have 0, 1, and 2, still 1 plus 1 is in the set. Still 0 plus 1 is in the set. Works for all of them, including the maximum. But this is what it means to be in the natural numbers, right? And so these two taken together, run infinitely many times, the inductive step, defines what the natural numbers hold. So starting with 0, you can get 1. You know that 1, you can prove using the inductive step that 1 must be a natural number, 2 is a natural number. So that's how you build the set. That's kind of cool. All right, so the last thing I want to show you today is a fun little proof. We won't get through it the whole during the time that we have, but we'll start it. It's a silly little graphical proof. It's one I stole from some MIT lectures. It's a cool one. So it's about L-shaped tiles and like growing crops in tiles of. Let's pretend we can grow crops in tiles that are L's. So Well, let's pretend that Fresno State is experimenting with some fancy kinds of corn, because they love to grow corn there. So they're experimenting with state-of-the-art corn that grows in an L shape. It looks like this. Your tracts of corn, they look like this. Right? You can grow as many of them, and you can put them in any way, but like this is an L-shaped tile of corn. All right? And Fresno State plans to use a 2n by 2n plot of squares to grow the corn, because like there's each tile takes up, that's 3 squares total. They're going to use 2n by 2n grid to grow their corn, and they want to make sure, like if you fill out your 2n by 2n grid of, you're going to put in L-shaped tiles of corn, like here's one right here maybe, here's another right here maybe. You can orient them anyway, but that's how they got to grow. They want to fill in their 2n by 2n plot with corn, and they also want to leave a square out in the middle for a sprinkler. All right, that's where they're going to put it. They're going to put it in the middle because then you can make it circular, right? And they can just like sprinkle water on everybody. So that's the setup. And here's the theorem. We would like to prove that, like, here's an example where this is a, well, this is technically them filling in a 2 to the 1 by 2 to the 1 plot with corn, L-shaped corn tiles. And then, like, the middle is technically a corner in that case. But here, this is a 2 to the 3 by 2 to the 3 square plot of, like, farmland. And we're putting, here's a bunch of L-shaped corn in there, and there is room in the middle for a sprinkler. We want to prove that this is always true. We want to prove that even if they want to scale up for any n, there is a way to tile, that is fill in, a 2n by 2n plot with your L-shaped corn while leaving out a 1 by 1 square somewhere in the center. You know it'll never be perfectly in the center, but like one of these guys. All right? That's what we would like to prove. All right? It's cool because mathematical induction will give us this proof, even though it's like pictures. Let me show that to you. We're going to run into a problem first, though. Like here's our normal original theorem. This is going to give us a cool thing to think about. But this is like, here's the original theorem, right? Theorem for all n, there is a way to tile a 2n by 2n plot with L-shaped corn while leaving out a 1 by 1 square in the center. Okay. This is your p of n, right? This is your predicate from here to here. This is your predicate p of n. Hope you see that. Like you got to show that p of 0 is true, p of 1 is true, p of 2 is true, all those things. We're going to use it. We're going to prove this using induction. All right. So what does that mean? In order to use induction, we need base case p of 0, then inductive step p of k implies p of k plus 1 for all k. All right. So our base case, we have that's when n is 0. We got to show that p of 0 is true. That's like you got to show that you can tile a 2 to the 0 by 2 to the 0 plot with your L-shaped corn with 1 square left over for a sprinkler. Well, if you have a 2 to the 0 by 2 to the 0 plot of squares, you can put no corn there, and right in the middle, the 1 square, you can put your sprinkler. Okay? So that is a proof of your base case. You can tile it, just don't put any corn at all, it doesn't fit. And then you put your 1 sprinkler, that's fine. And then the inductive step, we got to prove, inductive step, is that p of k implies p of k plus 1. All right, so we get to assume this one. We get to assume this one. That's our inductive hypothesis. It's a direct proof. And we're got to show this one. So this is the thing we need to show. And this proof is sadly going to fall through. There's an uh-oh moment. So what does it mean to assume p of k? Well, assume that there's a way to tile a 2 to the k by 2 to the k plot. Assume we can, there's kind of the proof, right? Here's us getting started on it at least. We assume we can tile a 2 to the k by 2 to the k plot with our L-shaped corn. What we need to show is that we can tile a 2 to the k plus 1 by 2 to the k plus 1 plot, because that's plugging in k plus 1, right? I need to show, I can't draw W right now for some reason. I need to show we can tile a 2 to the k plus 1 times 2 to the k plus 1 plot. Right, but we can use this as firepower. So let's break it down. In general, if you have a 2 to the k plus 1 times 2 to the k plus 1 plot. It's kind of cute that it'll break down into groups of 2 to the k by 2 to the k. Assume this is 2 to the k plus 1 tiles of corn, squares. This is also 2 to the k plus 1. Look at how, if you split it in half, right, that's just 2 to the k, twice. Split it in half another way, that's again 2 to the k. So do you see how this is like, this is 2 to the k right here, this is another 2 to the k, it's 2 of them, that makes 2 of k plus 1. So you do have your inductive hypothesis, you can use it. You find some smaller 2 to the k by 2 to the k plots. These are all 2 to the k by 2 to the k plots. See that? You got 4 of them total. And, all right, we're trying to show that we can tile using our L-shaped corn with one square left out in the center. We're trying to show that we can use this whole plot for corn. All right, trying to show that. We get to assume that we can tile every 2 to the k by 2 to the k plot with leaving a 1 by 1 square out in the center, right? So this means we can use our inductive hypothesis on each of these smaller squares, right? Because they're all 2 to the k by 2 to the k. We say we can do this for 2 to the k by 2 to the k. So that means we can tile this guy in some weird way, there's a way, while leaving out a square in the center for a sprinkler. We can tile this guy, you can do all that you want with our L-shaped corn in some weird way, and we can always leave out a square in the center of that 2 to the k by 2 to the k plot for a sprinkler. Like maybe it's over here, or it's over here, or it's over here, and it's over here. We can always put a sprinkler there. All right, you see that? So like that's what our inductive hypothesis gives us. Like we know that. We know that is true. We can get that by assumption. But our goal is to tile this whole darn thing with corn and leave out a square in the center of that for a sprinkler, like maybe this one. It's got to be one of the corners. Like we needed this one to be able to have the sprinkler. But our inductive hypothesis told us about these plots, and the center of those can have the sprinkler. See how that tells us nothing about that we can put one in the corner? Kind of want to put one in the corner of those. See that? So that actually is going to ruin it for us. This proof is not going to work. It is a true theorem. It is true that you can tile any 2 to the n by 2 to the n plot of corn like this, leaving out a square in the center for a sprinkler. That is totally possible. But sadly, I don't know why this isn't centered. But sadly, well, our theorem isn't good enough right now. All right, we have all this. Our assumption is not strong enough. See that? Like we wanted to leave out a square in kind of the corner of one of the other ones, one of the smaller ones. So this wasn't good enough to know that we can leave one out in the center. That was the problem. That is our uh-oh. Okay? That led to an uh-oh. So this is round 1 of the proof. There is a way to prove it. There is a way to prove it using induction. We're going to have to change the theorem, though. We're going to have to make it stronger. Because we want to put the sprinkler not just in the middle, really. Because we want to be able to move it like from there to there. See that? And like we want to get rid of 3 of these other sprinklers too. Just like leave the one and move it there, kind of. So that's our goal. It's a fun, cute little idea of a proof, and it really is true. This theorem, it really is true, and we're going to prove it by making a stronger inductive hypothesis. We're going to make a happy face in the end. All right, but that's where I want to stop for the day. Induction is difficult. It is a hard topic, and I don't want to melt your mind too much. But that's a good start, and so we'll come back here next time and continue.